Namaste and welcome again to another lecture on linear algebra through geometry. Uh, in this module we will be looking at the idea of linear equations in three unknowns, and we will also look at the idea of uh, LU decomposition. We look at the idea of least squares, then we look at inner products, which we have already seen in 2D. Even in 3D we have looked at dot products and inner products, and we are going to look at Gram-Schmidt orthogonalization and orthonormalization, of course, and we will also look at the idea of QR decomposition followed by eigenvalues and eigenvectors, basically the idea of eigen values and eigenvectors in 3D, which we had a very brief idea about in the last module. Of course, in the last module we actually looked at the concept of linear maps. We looked at the determinants and in terms of the volumes and stuff, and we also looked at determinants of various linear maps. We very intuitively looked at the idea of eigenvalues and eigenvectors, especially we focused on two important ideas there, that of reflection, how we intuitively got the eigenvalues to be say plus or minus 1 in terms of reflection, I mean the eigenvalues for the reflection transformation. And we also saw in the last module that how if you look at rotation transformation, when we saw rotation in 2 dimension, we figured out that the purpose of the rotation transformation itself is to reorient any vector that is given as the input to this transformation, which means the direction of the resultant vector is going to be different from that of the input vector that you had. But however, we saw that in case of 3 dimension it is actually a different game, that you are going to rotate about let us say a particular axis, and we also saw that in the last lecture, like if you look at, you are going to rotate about this axis, the rotation is happening about a plane, and that is exactly what we were looking at in the last class. And towards the end of the last class we said that we will try to look at the idea of linear equations in 3 unknowns. It is a bit slightly different here in this case. We are going to look at 3 equations and 3 unknowns. In case of 2 dimension we actually looked at the idea of linear equations in 2 variables, 2 equations and 2 variables. There we figured out that the system of 2 linear equations can have a unique solution, infinitely many solutions, or no solution, corresponding to lines intersecting at exactly one point, overlapping lines, and lines that go parallel which do not intersect at all. And we also looked at it from the column perspective, or from the idea of vectors, how we are going to represent such systems of linear equations vector in a vector format, where we said that if you are going to populate the matrix with the coefficients of let us say the 2 equations that you have, the coefficients of the unknowns in the 2 equations, we are going to put them as put them in a matrix, and you have the right side vector, which is a 2 component vector. Again, all we are looking for is scalars, let us say x1 and x2, such that the right hand side vector that you have, which is basically the B vector, we were looking at writing the right hand side vector as a linear combination of the columns of the matrix A. In this case the columns of the matrix A are going to be 2 component vectors, and there are only 2 vectors that is going to be there, because we are looking at a 2 by 2 matrix, alright. And that is where we got into it. Let us just recall that and then go ahead with looking at the idea of system of equations in 3 unknowns. We are going to look at 3 equations and 3 unknowns. So let us get on to it. Okay. So let us do this recall. In if x1 and x2 are 2 unknowns, and a11 x1 plus a12 x2 is equal to b1, a21 x1 plus A2 to x2 is equal to B2 are set of two equations. In these two unknowns x1 and x2, we said that solving for x1 and x2 is the same as finding the scalars x1 and x2. Okay, I will just make a small change here. We will say that solving for x1 x2 to satisfy the two equations simultaneously, solving for x1 and x2 to satisfy the two equations simultaneously is the same as finding the scalars x1 and x2 such that x1 and x2 such that x1 into A11 A21 plus x2 into A12 A22 is equal to B1 B2. That means finding the scalars such that we write the right hand side vector that we have, which is basically the B vector, as the linear combinations of the two component vectors, namely A1 the vector whose components are A11 A21 and the other vector A12 A22, which we actually captured in terms of matrix. We actually looked at this as Ax is equal to B, where our A was basically the coefficient matrix A11 A1 A21 A12 A22. This is what we had, and the vector x was basically x1 x2 and the vector b was b1 b2. This is what we had, and we had some more discussions on this. We said that if A11 and this vector, let us call this vector as, let us say, the A1 vector, and let us call this vector as the A2 vector. So, we said where A1 vector is corresponding to the first column of this matrix A, this corresponds to my A1 vector and this corresponds to my A2 vector. That is exactly what we had. So, what we said was if this A1 vector and A2 vector are linearly independent vectors, then for every B vector that you have on the right hand side, we can find a unique pair x1 x2 such that the right hand side vector B can be expressed as linear combination of the two vectors A1 and A2, right. And if in case the A1 vector and the A2 vector are linearly dependent, that means one is the scalar multiple of the other, then we said for B1 B2, which can be expressed as the linear combination of these two vectors, there will have infinitely many possible linear combinations corresponding to infinitely many values of x1 and x2, the scalars x1 and x2. And suppose if B1 B2 were not in the direction of A11 the vector A1 and A2, when A1 and A2 are linearly dependent vectors, we said that you cannot find scalars x1 and x2 which will help us get the resultant B vector as the linear combination of the two column vectors corresponding to the two columns of the matrix A. And if you recall, we actually did that in form of a sketch. We said that if you want to have if there is going to be unique solution, let us take this as along the E1 direction and let us take this along the E2 direction. We said that if this vector is, like, say, A1 and let us take this vector to be A2, then we can always find a B vector which can be expressed as B is equal to x1 into A1 vector plus x2 into A2 vector, and we said that in this case we have unique solution for every B. unique solution for every B, right. That means you can find a unique pair x1 and x2 such that this is possible. And we also looked at the other case where we said that okay, if you have the same thing E1 axis and you have this E2 axis, and let us assume that my A1 vector is here and my A2 vector is also here in the same direction. Let me call this as A1 vector and let me say this as A2 vector. We said that if B vector is going to be the along the same direction, we are going to have infinitely many solutions. That means you can find infinitely many scalars x1 and x2 such that B can be written as linear combination of A1 and A2. And the last case was even more interesting because it was looking like this, E1 and that is E2. Then what did we say? We say that okay, you have the A1 vector here and let us say I have my A2 vector also in the same direction, and if you have this B vector which is in a totally different direction, we said that this corresponds to the case of no solution. And we also had another understanding here that in both these cases the determinant of A, the 2 by 2 matrix that we had, was basically 0 in both these cases, right. Now what we are going to do is we are going to look at the same thing in terms of 3 equations and 3 unknowns. We will see how the geometry is going to be, and we will try to understand geometrically when we will have unique solution, when we will have no solution, and when we will have infinitely many solution case. This is what we are going to look at now. Okay. Okay, so let us look at this. Okay, okay, let us first of all take this up. Suppose we have the following system of equations. The following system of linear equations in 3 unknowns. Right. So I am going to have A11 x1 plus A12 x2 plus A13 x3 is equal to B1, A21 x1 plus A22 x2 plus A23 x3 is equal to B2, A31 x1 plus A32 x2 plus A33 x3 is equal to B3. This is what we have, and we say that solve for x1, x2, x3, solve for x1, x2, x3. Now how do we interpret this? We again write the matrix form of this, where I am going to write this in the form of Ax is equal to B, where my A matrix is going to be the coefficient matrix, which is going to be the 3 by 3 matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. X is the 3 component vector that we have, which is x1, x2, x3, and B is again another 3 component vector, which is B1, B2 and B3, right. Now recall that in 2 dimension case we did something. We made an interesting observation here. In case of 2 dimension, we said that whenever you have infinitely many solution or no solution, the determinant of A was 0, and in this case the determinant, whenever you had unique solution, we said that determinant of A is not equal to 0, right. This determinant of A equal to 0, infinitely many solution and no solution, depends on what kind of B that we have, that it depends on the B vector, and we are going to take the same ideas in 3D, and we are going to say that if, let me say, A1, A2 and A3, that is A1 vector is basically the first column of the matrix A, which is A11, A12, A21, A11, A21, A31. The A2 vector is basically A12, A22, A32, and the A3 vector is this A13, A23, A33. So, we say that if A1, A2, A3 are truly in 3D, or let us just put R, okay, R in 3, okay, R in truly in 3D, in the sense that you have the 3 vectors to be in totally 3 different directions. You can have 2 of them, you will have 2 of them to be in a plane, and then one in a completely different direction which is not in the plane. So, if that is the case, that is exactly why we call it like truly in 3D. In a sense, what it means is, if these 3 vectors are, when we say truly in 3D, we tend to imply that if you can form a tetrahedron with this 3 vectors, then you say that the volume of this tetrahedron, or the volume of the parallelepiped that you would actually get, is going to be non-zero, in which case, as we have already seen, you can look at inversion, the matrix inversion stuff, and stuff, and whenever the determinant was not equal to 0, we always got a unique solution. So, that is the understanding that we get from our 2D. So, and we are going to follow the same thing. So, we are saying that are such that if A1, A2, A3 are such that they form a tetrahedron, then for every B, in 3D, we will have unique solution. We will have a unique triplet, unique solution, or x1, x2, x3. Is that okay? Essentially what we are trying to say is, like, you are going to have base to be a triangle, and then you are going to have the third vector which is going to be the along a different direction, and in a sense you can actually do the same thing like what you did in 2D, where we constructed a parallelogram. Now we are going to construct a parallelepiped, therefore you will see that the volume of the parallelepiped is non-zero. If that happens, we will have this. So, what we are going to say is, this implies if determinant of A is not equal to 0, then we have unique solution corresponding to x1, x2, x3 corresponding to every B in 3D space, right? Is that fine? So, that is what we are going to look at right now. So, the idea is, if you have unique solution, I mean if you have the let us see geometrically like how that looks. So, let us look at that, that is even better. So, we are going to have this, let us assume that these are the 3 axes that we have. Let us say E1 axis, let us say the E2, and then we have E3. Let us assume that there are 3 vectors, namely this is my A1 vector, and let us take that to be the A2 vector, and let me take this, sorry, let me take this to be the A3 vector. Then what we see is, like, you can actually I mean this 3 are in 3 different directions. So, we have already seen that we could construct a parallelogram. Now, what happens is wherever your B, suppose I have this to be my B vector, in this case we can write B to be a linear combination of these vectors, namely x 1 into a 1 plus x 2 into a 2 plus x 3 into a 3. You change the B, you basically get a different x 1, x 2, x 3, that is exactly what it means, right. So, that is what it means. Now, what we are going to do is we will see like what is it to say that we do not have I mean we do not have unique solution, or we are going to have infinitely many solutions or no solution. So, let us just look at what that means, right. Okay. So, let us look at this. This corresponds to the case of unique solution in 3D, unique solution to A 3 cross 3, x 3 cross 1, B is that okay. So, this is what it is going to be. Now, let us look at the other case. Let us look at the case. Okay. So, what is it to say? It to say Ax equal to B has infinitely many solutions. Infinitely many solutions where A is a 3 by 3 matrix. A is basically as given, we know this, A21, A22, A23, A31, A32, A33, X is basically this X1, X2, X3, and B is equal to B1, B2, B3. Yeah. So, if this is the case, so the question is if this is the case, then we are going to again ask the same, like what is it to say infinitely many solution. How did we tell that we have infinitely many solutions in case of 2D? We said that if you take a 2 by 2 matrix and you have 2 columns of the matrix, basically the 2 column vectors, if they are in the same direction and B is along the same direction, then we are going to say that there is going to be I mean you are going to have infinitely many solutions. That is exactly what we are going to say. So, we are going to say that geometrically how does this look like? So, the first thing that we had that we looked at in 2D when we said we had infinitely many solution is that the since the column vectors are in the same direction, we said that the determinant of that matrix 2 by 2 matrix is 0. If you recall, which we just wrote some time back, we said that the determinant of A is 0, that means A1 and A2 are in the same direction, or A1 and A2 are scalar multiples of one another, and B is also the same direction or A1 A2. If that is the case, then we said the determinant of A is 0. That is exactly what we are going to look at here. So, we are going to say that if we are going to have the same thing, which means in this case first condition is the determinant of A is equal to 0. If the determinant of A is equal to 0, then there is a chance that the system of equations may have infinitely many solutions, or it will have no solution at all. Again it is what we had in the case of 2D. So, we will try to figure out geometrically how does this case of infinitely many solutions, how is it represented in case of 3 dimension. Let us look at that, right. So, for example, when I say determinant of A is equal to 0, there are only 2 possibilities that can occur. you can have all these 3 vectors to be in the same direction, or the third vector, like one of these 3 vectors can be in the same in the plane that is formed by the other 2 vectors, right. We know that 2 vectors, we remember, if you remember it, we said that this vector E1 which is 1 0 and E2 which is 0 1 in 2D, the linear combination of this form the entire 2 dimensional space, and that was basically a plane. Now what we are going to do is we are going to say the same thing. If the determinant of A is 0, then there are 2 things that can happen, where all the 3 vectors are in the same directions, or one of the vectors is in the plane that is formed by the other 2 vectors, right. So determinant of A is equal to 0, there are 2 things here, let us see what they are. So the first thing is basically okay, suppose if I take this to be the A1 vector, okay, let us do that. First of all, let the vector A1 be equal to A11, A21, A31, A2 vector B is equal to A12, A22, A32, and A3 vector is A13, A23 and A33. So we have this, right. So what is the thing, when can determinant of A be equal to 0? Determinant of A is 0 if, so determinant of A is 0 1 if all the 3 vectors A1, A2, A3 are all 0 vectors, which is not what we are looking at, right. We have A1, the vector A1 is equal to the vector A2 is equal to the vector A3 is equal to the 0 vector. That means all the columns of the matrix A matrix are all 0, that will happen. I mean, if that is the case, then the determinant is 0. The second case is A1, let us say, is k multiple of A2, and A1 is also, let us say some L multiple of A3, right, or yeah. So or you can probably write this as the other way of doing it is like, okay, anyway, which means you have A1, A2, A3 to be, you know, they are all multiples of one vector. So that is what we are going to have. So we are going to, if this is case, each vector is going to be multiple of the other, in which case determinant of A is 0, and in the third case we are going to say the vector A3 is going to be, say, some alpha times A1 vector plus beta times the A2 vector, which means A3 vector is basically a linear combination of the other 2 vectors A1 and A2. If one of these 3 cases happen, or even one of the vectors is 0, in which case one of them, okay, one or many of them is 0, okay, one, let us say at least one of them is 0 vector, in this case at least one is a 0 vector, right. That is the case, then we have this, right. So how does this look like? So let us just take the third case, because that will be a bit more interesting, because we do not want to look at the case where we have all the column vectors to be the 0 vectors, because the matrix itself is 0 matrix. So what we want to do is we want to look at the other 2 cases where all 3 columns are in the same direction, or one of the vectors is going to be in the plane that is formed by the other 2 vectors. So if that is the case, geometrically how is it going to look like? So let us take this. So we have this E1 axis, we have this E2 axis, and we have this E3 axis. Now let us see what happens. So we are going to have this to be the A1 vector, and let us take this to be the A2 vector, and what we are going to do is we are going to do something interesting here. A3 vector is also in the same plane as the A1 A2 vector, and what is interesting is our B vector is also in the same plane as the A1 A2 A3 vector, which means essentially it is going to look like this. Say suppose I have a plane which is like this, suppose I have a plane which is like this. Let us say that I have my a1 vector, I have my a2 vector, I have this a3 vector and b vector is also here. So, you have a1 vector, a2 vector, a3 vector and b vector. So, if this is the case, that means b is also something which can be expressed as a linear combination of those two vectors a1 and a2, then we say infinitely many solutions case. This is the case corresponds to infinitely many solutions. What does this mean? This means one of the two vectors, we can put it this way, why one of the two vectors? We will say that all the 4 vectors all the 4 vectors a1, a2, a3 and b are all in the same plane, in the same plane. So, infinitely many solution corresponds to this scenario. Now, what happens to the case of no solution? So, no solutions case. So, how do we interpret no solutions case? That is again simple. We said that even the no solutions case from our 2-dimensional understanding, 2D understanding is that determinant of A must be 0, which means we are going to look at the same case where in which we have all the 3 vectors to be in the same plane. So, we are going to look at this. So, I have my E1 axis, E2 and then E3 axis and A vector, this is the A1 vector and that is the A2 vector and let us say this is the A3 vector and let us take this to be my A4, I mean the B vector. Essentially what does this mean? Okay, sorry, if this happens, then you have infinitely many solutions. Let us take this is the E2 axis, this is the E2 axis. Now, where is the B vector sitting? The B vector is out of this plane, let us say this B vector is here, right. If this is the case, then the B vector does not belong to, or it is not a vector which is on the plane which is spanned by these 3 vectors, say A1, A2, A3, B is outside of the plane and therefore, we have no solution. So, essentially how does this look like? It is again going to, let us write the, let us draw it and then check. So, let us take this, I have my A1, I have my A2 vector, I have A3 vector. So, this is A1, that is A2 and that is my A3 vector, and where does this B vector sit? The B vector is going to sit somewhere outside, the B vector is like this. For example, let us assume, so for example, if A1 vector is basically let us say 1, 2, 0, A2 vector is basically let us say 2, 3, 0 and my A3 vector is let us say 3, 5, 0 and my B vector is say 0, 0, 1. It is very clear that if you see here, the vector A1, A2, A3, the 3 vectors are there in the x1, x2 plane, the third component is 0, the third component of each of those 3 vectors is 0. That means these 3 fellows are in the same plane which is corresponding to the x1, x2 plane, whereas the vector B that you see here, the vector B is basically it is along the x3 axis because only that component is 1. So, it is along the x3 axis, therefore, this B vector is not in that x1 x2 plane, therefore, this B vector that you have here cannot be expressed as linear combination of the 3 vectors a1 a2 a3, and therefore, this system of equations. So, the corresponding system of equation in this case is going to be 1 2 0 2 3 0 3 5 0, let us say x1 x2 x3 is equal to 0 0 1. It is very clearly, if you look at the 0 x1 plus 0 x2 plus 0 x3, the last equation is going to give me 1. So, this corresponds to an inconsistent system, right, inconsistent system. So, if you look at what would you call, if you look at a 3 by 3 system of equations, that means 3 equations 3 unknowns, we have the same case as unique. So, we are trying to solve for a system of equations with 3 unknowns, and there are 3 equations. There can be 3 situations here. One is a situation of unique solution where you find that the 3 vectors that you have, which corresponds to the 3 different columns of the matrix A, the 3 columns of the matrix A basically they form let us say a tetrahedron in 3D, and you see that the parallelepiped that is formed has a finite value, it is a non-zero value, and therefore, you will have unique solution for every right hand side B vector that you have. So, Ax equal to B will have unique solution. And when you look at infinitely many solution, you have 3 equations 3 unknowns, and correspondingly you have a matrix of 3 columns 3 rows, and you have a right hand side vector B. And what we see here is that suppose if you say infinitely many solutions, this basically corresponds to the case where the determinant of the matrix is 0. If the determinant of the matrix is 0, then there is no volume formed, there is no 3D structure that is formed. All you get is a parallelogram, basically the 3 vectors will span a plane, and therefore, the area of the volume of the parallelepiped is going to be 0, in which case you will have infinitely many solution if the right hand side B vector is also in the plane, same plane that is spanned by the 3 vectors which correspond to the 3 columns of the matrix A. And the case of no solution will arise if you have again the determinant of A to be 0, but only thing there is the vector B is not going to be in the plane that is spanned by the 3 vectors which corresponds to the 3 columns of the matrix A, if the matrix A is going to be a 3 by 3 matrix. So, that is exactly where we get into the idea of inconsistent system and system with no solution. So, in the next class what we will be doing is we will be looking at homogeneous system of equations in 3D. Of course, we will be looking at the case of non-trivial solution, because trivial solution is always there for a homogeneous system of equations. So, we look at non-trivial solution. How does that system of equation look in our in the idea of vectors that we are going to look at. We will follow it up with solving system of equations using Gauss elimination. We are going to revisit this because you have already done that in your module 1. So, module 1 and module 2. So, we are going to revisit this because in the light of having studied linear transformations being applied over vectors, we are going to look at linear transformations being applied over matrices now. We are going to look at the 3 elementary row operations which we did in the module 2. We are going to look at that in terms of linear transformations of vectors. We are going to look at same shear, reflection, and scaling. We are going to look at that, follow it up with the LU decomposition. So, that will be the agenda for the next class, and we will follow it up with least squared solutions where we are trying to find out an approximate solution when there is no solution, and we are going to look at what is called as the Gram-Schmidt orthonormalization process, follow it up with QR decomposition of a matrix A, and then take up eigenvalues, eigenvectors in A. With that, we will actually be concluding the entire 2-dimensional perspective and 3-dimensional perspective of the visualizations and stuff, geometry and things. And what we will do is in the following week onwards, we will start with general vector spaces, linear vector spaces, We will look at ideas of vector spaces. We will generalize all these results. We will put all of them across in a very systematic way, and we will try to gain the mathematical insights for higher dimension. Thank you.